Welcome to this explainer. If you're tuning in today, it means you're serious about mastering physics. And honestly, that is exactly what I expect. We're going to treat this session like a real strict, no-nonsense classroom environment. Why? Because we are here to truly conquer NCERT physics step by step. We are absolutely not going to just blindly memorize a bunch of facts and formulas, okay? We're going to build your conceptual foundations so strongly that you won't just pass your Class 9 exams, you are literally going to ace them. So grab your notebooks, get focused, and let's get straight to work.
All right, here is our exact game plan for today. 1. Defining force and its units. 2. Balanced versus unbalanced forces. 3. Newton's first law. 4. Mass inertia and some real-world examples. 5. Tackling exam numericals and avoiding common traps. And finally, 6. A rapid-fire chapter revision.
Okay, Section 1. Defining force and units. You know, you really can't build a house without a solid foundation, and you definitely can't understand motion without grasping exactly what a force actually is.
So, what is a force? Essentially, it's an external cause. It changes, or even just tries to change, four specific things: the state of rest, the state of motion, the direction of motion, or the shake of a body. And please, whatever you do, do not forget this absolutely crucial detail. Force is a vector quantity. That means it isn't just about how much force you apply, the magnitude, it's also about the exact direction you're applying it in. I mean, without a specific direction, you just don't have a force. Make sure you have that crystal clear in your head before we move on. We good? Okay, let's keep going.
And this brings us right to the mathematical backbone of our entire chapter. F equals ma. Force equals mass times acceleration. Honestly, write this down, highlight it, put a huge star next to it. If you have the mass of an object and you know exactly how much it's accelerating, you can calculate the exact force acting on it. This simple little equation is your absolute master key for solving numerical problems.
Now pay very close attention to this number, 10 to the power of 5. You all probably know the SI unit of force is the Newton, but examiners absolutely love testing your deeper knowledge by asking for the CGS unit, which is the dyne. 1 Newton is exactly equal to 10 to the power of 5 dyne. This is a classic textbook multiple-choice question. Seriously, do not let them trick you out of such an easy mark.
Moving right along to Section 2, Balanced versus Unbalanced Forces. I need your full, undivided attention here, because confusing the effects of these two is hands down the #1 conceptual error I see students make year after year.
Let's just contrast these directly so we never mix them up. First up, balanced forces. Here, the net force is 0. Now listen carefully to this. A balanced force does not just mean an object is completely stationary. Actually, it just means there's 0 acceleration. If an object happens to be at rest, sure, it stays at rest. But if it's already moving, it keeps moving in uniform motion, meaning its velocity remains completely constant. On the flip side, we have unbalanced forces. This means the net force is not 0. And this is where the magic happens, right? An unbalanced force is what actually produces a change in speed or direction. It actively accelerates the body. Do you see that difference? It's 0 acceleration versus an actual change in speed or direction.
Which brings us perfectly to Section 3, Newton's first law. Basically, everything we literally just discussed about balanced and unbalanced forces culminates right here.
I want you to memorize this concept, and I mean really understand it, not just parrot the words. An object remains in the state of rest or of uniform motion unless compelled to change that state by an applied external force. This law is basically the direct, theoretical result of an object experiencing 0 net unbalanced force. If the forces on something are perfectly balanced, the object just casually keeps doing exactly what it was already doing. To change its reality, you have to apply an unbalanced external force. That, right there, is Newton's first law in its absolute purest form.
Let's jump into Section 4, Mass, Inertia, and Examples. It's time to see how this builds into real-world applications. Because physics isn't just a bunch of abstract equations on a chalkboard. It is literally the world happening all around you. We have to apply this stuff so we don't fall into the trap of blind memorization.
So, here is a super classic NCERT question for you. Picture it. You're standing up in a moving bus, right? Suddenly, the driver slams on the brakes and you stumble forward. Why does that happen? I want you to actively think about the reasoning for a second. What exactly is happening to your body compared to what's happening to the bus? Well, the answer is inertia. Inertia is just the natural tendency of an object to resist any change in its state of rest or uniform motion. Think about it. Your body was already in motion along with the bus. The bus stopped, but your body, it wanted to keep right on moving forward. And how do we actually measure this physical resistance? We use mass. Mass is the exact measure of inertia. This means a massive, heavy truck inherently possesses way more inertia, way more resistance to changing its motion than a much lighter motorcycle. Or, exactly as your textbook puts it, a heavy stone has more inertia than a small rubber ball.
And here is exactly how they're going to test you on this. There are 3 specific types of inertia, and you absolutely must map them to their exact NCERT examples. First, we have inertia of rest. This is exactly why dust comes flying out of a beaten carpet, or why leaves detach when you vigorously shake a tree branch. The branch moves, but the leaves resist that sudden motion. Second, inertia of motion. This is exactly what we just talked about with the bus passengers falling forward when it brakes. And third, inertia of direction. Imagine you spin a stone tied to a string and then suddenly let it go. It doesn't keep circling, it flies off tangentially in a perfectly straight line, because it's actively resisting a change in its direction. You really need to lock these specific examples firmly in your memory.
All right, Section 5, Exam Numericals and Traps. We are entering the real crucible of the lesson now. Concepts are fantastic, but your exams are going to require you to do some actual mathematical application. So I need you to pay very, very close attention to how we take this theory and apply it to numerical problems.
Okay, here is your definitive chronological blueprint for solving force numericals without making those silly, careless errors. Step 1. Always extract your givens from the text first. Write down your mass m, initial velocity u, final velocity v, and time t. Step 2. Find the acceleration using that classic kinematics formula, a equals v minus u, all divided by t. And hey, here is where my error analysis comes in for you. Do not misread the question and accidentally mix up your initial velocity u with your final velocity v. If a car eventually comes to rest, that means the final velocity v is 0. Got it? Step 3. Once you finally have a, you simply plug it right into F equals ma. It's a very structured progression. If you follow it strictly every time, you won't go wrong.
Now take a really good look at this number, 1,000. Why am I telling you this is a massive conceptual trap? Well, because in your exams, they love to throw the classic truck rolling down a hill problem at you. And they'll state its mass is, say, 7 tons. Listen to me. If you plug the number 7 directly into your F equals ma equation, your entire calculation is instantly wrong. Gone. 1 ton equals 1,000 kilograms. You absolutely must convert those tons to kilograms before calculating your force. Please, don't lose precious points on simple unit conversions.
Let's tackle just one more common trap, but this time it's visual. If an examiner tells you the net force on an object is 0, and then asks you to visualize that on a velocity time graph, what does it actually look like? Well, it's just a straight, flat, horizontal line. Why is that? Because if the force is 0, the acceleration has to be 0. And if acceleration is 0, your velocity remains perfectly 100% constant. It doesn't go up, it doesn't go down, it just stays perfectly flat as time moves forward.
And finally, Section 6, Final Chapter Revision. We have covered the solid foundation, the conceptual laws, and all those sneaky mathematical traps. Right now, I need your absolute total focus for this final rapid-fire chapter revision so we can permanently lock all this knowledge into your brain.
Okay, here is your ultimate one-page summary. Take a mental snapshot of this right now. Force is a vector, and it's calculated by F equals ma. 1 Newton equals 10 to the power of 5 dyne. Balanced forces mean the net force is 0, which immediately translates to 0 acceleration. Newton's first law, that is essentially just the law of inertia. Mass is the direct physical measure of that inertia, meaning a bigger mass gives you a bigger resistance to change. And mathematically speaking, always remember to convert your tons to kilograms and your kilometers per hour into meters per second. Now, right before we wrap up this explainer, I want to leave you with a bit of a provocative thought based on everything we've just learned. When a batsman hits a cricket ball, it rolls along the ground and eventually it just comes to a stop, right? But according to Newton's first law, it should literally keep moving forever. So what exactly is the invisible, unbalanced external force acting on that ball, actively opposing its motion and forcing it to stop? Think about that, use your new rock-solid foundation to answer it, and I will see you in the next lesson.